Good afternoon. I'm very impressed that Professor Lowe's models work in practice as well as in theory, insofar as we've got a larger crowd here today than we did yesterday, so there's clearly learning of exactly the sort that he predicted, namely good information encourages growth. And the subject of his talk yesterday was to set out a model of evolution, which is going to be the basis of his talks in this series. Yesterday he described a model which comes up with results that are quite at variance with traditional economics in many respects, in emphasizing the importance of diversification in the context of populations that are concerned about their survival and growth. And in particular, he mentioned the fact that probability matching, which is very difficult to explain in conventional economics terms, has a natural resolution in the context of evolutionary models. And he tantalizingly said at the end of his lecture yesterday that these evolution models will provide a resolution of some of the key paradoxes in finance. And on that basis, I'll ask Professor Lowe to come forward and deliver his second lecture on adaptive markets in theory and practice.
Well, thank you, Colin, for that terrific introduction and summary. And I want to thank all of you, particularly those of you who were here yesterday, to come back for more. Those of you who were here yesterday, you remember that we went through some fairly detailed calculations for the underlying basis for the adaptive markets hypothesis, in particular the binary choice model, where we use the principle of natural selection to demonstrate that certain kinds of behaviors emerge organically, purely from natural selection, without any kind of strategic optimization or utility maximization. And this is a rather significant departure from standard economic theory, but one that my co-authors and I find quite natural, and I hope you will as well as we describe some of the implications. What I want to do today is to take that as the launching platform for a couple of extensions. One is to focus on bounded rationality. We now understand that behavior can look irrational from the individual perspective, but could actually be quite sensible from the population perspective. But what does that say about the kind of behaviors that we as humans engage in? The binary choice model is a very, very simplistic version of what we consider to be complex economic decision making. So I want to focus on that today and then take you through a rather extensive detour through the cognitive neurosciences to see how some of these mathematical models actually have some physiological and neurobiological underpinnings. So this is not going to be nearly as trying as yesterday. We're not going to have nearly as much maths. Somebody once told me that as an author, for every single equation you include in a book, you divide your audience by 2. And so by that count, some of my early work has maybe 2 or 3 readers in the world. I'm very, very worried about that. So I'm going to try to focus today on a broader exposition and actually engage the audience in some real-time experimentation. It won't hurt a bit, but hopefully you'll learn something, as I always do, from these experiments. So let me start with bounded rationality. Where we left off yesterday was that clearly there's a long literature that started with Herbert Simon, among others, about the fact that individuals don't make decisions in the way that mathematical economists typically propose. Now, you recall that Simon, in 1956, wrote a book called Models of Man. And before that, in 1947, when he published his PhD thesis on administrative behavior, Simon actually spent a fair bit of time studying how people make decisions, particularly corporate executives. Actually, his degree was not in economics or mathematics, it was in political science. And right from the beginning, he had suspicions about economic theory, despite the fact that he actually contributed to quite a bit of economic theory. But in 1956, he wrote a book called Models of Man, where he tried to formalize the idea of how people actually make decisions, as opposed to how economists hypothesize that they make decisions. And he came to develop an idea that he called satisficing. Now, satisficing is not a word that exists in the English language, at least not before Simon. He created it in order to come up with an alternative to optimizing behavior. His view was that humans do not maximize, do not optimize. They simply engage in heuristics that are good enough. Good enough meaning satisfactory. And that's where the word satisficing comes from. Now, he developed this notion not just from basic observation of how people make decisions, but he actually spent a fair bit of time studying decision-making from a computational perspective. In fact, Simon actually had more impact on computer science, particularly artificial intelligence, than on economics. You all, I suspect, know that Simon won a Nobel Prize in economics, but you probably didn't know that most economists at that time were both shocked and disgusted with that outcome. So much so that I've heard from people that were there at the time, when he was at Carnegie Mellon, he started out in the Graduate School of Industrial Administration, where all the economists were. But after a few years, he became disenchanted with economics and economists and decided to move to the psychology and computer science departments. And when he won his Nobel Prize in economics, he won it while he was a faculty member in those other departments. Naturally, Carnegie Mellon held a big party for him the day that the Nobel Prize was announced, and everybody was invited. And everybody came from the university except for his colleagues from the economics department. Not a single one of them showed up because they were so disgusted with the outcome. So it gives you a sense of the kind of controversy that he generated with his ideas. In fact, the reason that it was such a controversial idea was because he couldn't respond effectively to a critique of his that economists leveled immediately. Economists said, if you think that you engage in heuristics that are simply good enough, how do you know when good enough is to be left alone? How do you know when you reach that point that's good enough? In particular, suppose that you spend a little bit more time thinking about optimizing, even if you can't optimize to the global optimum. If you spend a bit more time trying to come up with a better solution, wouldn't that necessarily require that you understand whether or not the costs and benefits are equated? And if you are able to do that, then why can't you do what economists hypothesize you do, which is come to the rational expectations equilibrium? Simon didn't have a compelling retort, and frankly, I think that the answer is a lot simpler than we think. The proposed response that I would give today is that we, in fact, don't know when good enough has arrived. We simply behave in a way through trial and error based upon the environment and the kind of feedback we are given those environmental conditions. So I want to give you an example of how we apply this in a very, very simple context. We're going to apply evolutionary principles to heuristics, and then throughout the rest of this lecture, I'm going to bring in the neurosciences and then ultimately apply that to modeling financial dynamics. But let me give you an example of what I have in mind for how you can respond to Simon's critics about heuristics. And to do that, I'm going to give you a particular problem that I face every day, and I suspect all of you do, and show you what kind of heuristics I've developed in order to respond to that. It's getting dressed in the morning. We all have to get dressed in the morning, and in doing so, you have to decide what to wear for a particular occasion. So I had to decide very carefully, after great thought and consideration, what I was going to wear for today's lecture. Now, to give you a sense of what my optimization problem is as a rational economist, let me tell you what my wardrobe looks like. I've got 5 jackets, 10 pairs of pants, 20 ties, 10 shirts, 10 pairs of socks, 4 pairs of shoes, and 5 belts. Now, you might think that that's a rather limited wardrobe, but I'll have you know that this wardrobe implies that I have 2 million unique outfits. Just do the maths and multiply the combinatorics. Now, true, not all of my outfits are equally compelling from a fashion perspective. So I've got a decision to make. I've got a real decision problem, right? How do I pick just the right outfit that's suitable for today's event? So suppose that it takes me 1 second to evaluate the fashion content of a given outfit. Now, it actually takes me longer than that, but let's suppose it takes me a second. Well, how long would it take for me to get dressed? Well, if you do the multiplication, the answer is it would take me 23.1 days to get dressed. And I promise you, it doesn't take me nearly that long. So how do I do that? It's amazing, isn't it? It's amazing that we can get dressed so quickly, despite the fact that for any sensible mechanism for optimization, it would take us much longer time. Well, the answer, of course, is that we don't optimize. We use heuristics, rules of thumb. But where do we get them from? So I'll tell you a story that happened to me many years ago that gives you a sense of how I developed part of my heuristics about getting dressed in the morning. When I was 6 years old, I was in first grade in New York City, and at that time, some marketing genius discovered that if you took a Superman emblem and put it on a child's jacket, you could sell a lot of them to these young, impressionable kids. Because at that time, Superman was the superhero of the day. In fact, I think a movie just came out with Superman, so it's, he's apparently quite durable. So, of course, I desperately wanted a Superman jacket, and I nagged my mother, I think for weeks, literally weeks, that's what she told me, for weeks, to get it. Now, I grew up in a single-parent household, so we didn't have a lot of extra income, and this was a luxury that we couldn't afford. So that's why it took me weeks to nag my mother into agreeing to buy it for me. And so she did. Finally, she relented. And I remember the very day when that occurred. It was a Friday, and at the evening, after she came home from work, we went to the local department store, Alexander's on Queens Boulevard, and we got the jacket. And I put it on immediately, and I don't think I took it off for that entire weekend. I slept in it. I ate in it. I wanted to take a bath in it, but she wouldn't let me. I was so excited. Come Monday morning, I got up extra early, put the jacket on, walked in front of a mirror, looked at how I would look with this jacket, did all my action poses, and I spent so much time in front of the mirror, I ended up being late for school. Now, in those days, if you were late for school, you needed a note from your mother to get into the classroom. So I had to go to where my mother worked. I was 6 years old at the time, and it was not easy to do all of this. I went to get a note, and I walked into the classroom. Everybody was seated, working on their assignment. I had to walk to the back of the room, and everybody was looking at me, snickering that I was late, and I was so mortified. In fact, I was so mortified because that happened 45 years ago, and I remember it to this day. I remember what happened on that day. That I was never, ever late for school again. It never took me more than 5 minutes to get dressed, because I remembered from that one day, that experience changed the way that I got dressed. Now, that is one aspect of my heuristic. I take very little time to get dressed. In fact, I'll tell you a secret right now. I still feel this way. In the profession that we're in academia, how you dress is actually completely unimportant. In fact, if you spend too much time getting dressed and wearing nice things, you're actually looked at quite suspiciously by your colleagues in academia. However, I would argue that somebody like Tom Cruise, the movie star, spends a lot more time getting dressed each day, because for him, in his profession, in his environment, his heuristic has emerged and evolved quite differently. So that's an example of the response to Simon, which is we don't know that if we just spend a little bit more time optimizing, we might not get a better solution. That's true, we might, but we aren't inclined to do that unless the environment calls for it. So when I was in college, a friend of mine got married, and I was invited to be the best man, and I went to a rehearsal dinner, and I showed up in sneakers and jeans, and I realized that that's not a good thing to do. Even for a rehearsal dinner, you've got to dress up. So I learned a new heuristic on top of my old heuristic of getting dressed in 5 minutes. That's the response to Simon's critics. Trial and error coupled with selection in a particular environment, that changes how we behave. Now, what about intelligence and where that bound of rationality lies? Well, in order for us to understand the bounds to rationality, we have to understand what rationality and intelligence mean. So let me first ask you, what is the opposite of intelligence? When I tell you that somebody is completely unintelligent, what do you think of? Somebody who's stupid, right? Stupidity is the opposite of intelligent. So here are 3 examples of stupid behavior. So here's one where some people are partying in a pool, having a great time, and they've got the radio blaring here, but of course the radio is on a table, and they need to get power to the radio, so of course they have an extension cord. The extension cord is being floated by 2 slippers. What could possibly go wrong with this? Second example is a fellow who wants to get a close-up of the inside of an alligator's jaw. Now, this is funny, but this actually had a rather sad ending, as you can imagine. Somehow, something slipped, or something something tickled the crocodile's jaw, and he clamped down. And third, here's a truck driver. I don't know if you can see this image. Here's a truck driver fixing the bottom of his truck, and he decided to prop up the truck with a wooden pole here. Now, we laugh at this. These are all real photos, by the way, of people who are actually doing real things, really stupid things. And as part of the so-called Darwin Awards, a number of people win because they ultimately kill themselves by doing these stupid things. What we mean by intelligence is the opposite of this. In other words, behavior that confers a specific advantage to individuals, right? Because the opposite of that is this kind of behavior that's detrimental to your survival. If that's the case, then we have a very natural definition of what intelligence means. Intelligence is any kind of behavior that confers a reproductive advantage. Now, if you acknowledge that that's a useful definition of intelligence, then it turns out that yesterday's mathematical model of evolution can actually derive not only intelligent behavior, but bounds on that intelligence. Let me show you how. For those of you who weren't here yesterday, I'm going to just go through it very quickly. I apologize for that. You can take a look at yesterday's lecture, which is online, as well as the paper. So remember, from yesterday, the action that an individual engages in is simply 0 for choice A, or 1 for A and 0 for B. And yesterday, we assumed that it was mindless behavior. In other words, individuals were simply choosing A versus B, in some cases randomly, in some cases deterministically, and we were going to allow evolution to show us which of these different behaviors was going to emerge most successfully, the one that was going to grow the fastest. It turns out that the assumption that this behavior is statistically independent of the outcome is part of that mindlessness that we were focusing on yesterday. I'm now going to change that today. Suppose that instead of assuming that your actions are statistically independent of outcomes, what if, for whatever reason, there are certain individuals in this ecology for whom every time they choose A, that ends up being the situation where XA is greater than XB. And every time they choose XB, it just so happens that XB is greater than XA. In other words, suppose that individuals, for whatever reason, have correlation with outcomes. If you change this assumption and now allow individuals to have behavior that is correlated with X, that's intelligence. Well, I should be careful. If it's positively correlated, that's intelligence. If it's negatively correlated, that's stupidity, right? And so if we simply assert that the covariance of a particular individual happens to be positively correlated with the difference XIA minus XIB, that's enough to show that this individual will have a faster growth rate than those who do not have that correlation. So this captures the essence of intelligence. Now, I won't take you through the mathematics of it. It's actually not that complicated, but it looks a bit messy. But in this case, when we have correlation, we have a very interesting bottom line. The bottom line is that the growth rate of individuals with a given level of correlation rho is going to be equal to the growth rate without any correlation plus an extra term that's going to be the same sign as the correlation coefficient. If you have positive correlation, you're going to grow faster than those who don't. And if you have negative correlation, you're going to grow slower than those who don't. Now, if you have an expression that looks like this, you can optimize it as a function now of two variables. F, your behavior, and rho, your correlation. And rho is then a measure of intelligence. The bigger the rho, the more intelligent you are. The more ability you have to forecast which of your behaviors will have a good outcome in terms of reproductive success. So if you want to optimize that very simple equation, we have a very simple result. The optimum behavior is for the correlation to be 1, of course, and for F star to be the probability that XA is greater than XB. this is a surprising result because in this case, we only have idiosyncratic reproductive risk. And from yesterday's lecture, we know that with idiosyncratic reproductive risk, the optimal behavior is always to choose A. But in this case, you're going to do probability matching even though you only have idiosyncratic risk. It's because now there's a second variable, which is the correlation with your outcomes. Now, in general, you can't get correlation equal to 1. Right? There are certain physiological constraints that limit you from being able to predict perfectly what your reproductive success is going to be. So, in particular, the individual with the highest rho, whatever that is, will dominate. And now if we let rho, your predictive power, be a function of state variables, for example, it's a function of your cranial capacity, or it's a function of the particular environment that you're in. If you have night vision and it's nighttime, you can actually see farther than other creatures. Therefore, you can protect your offspring, which means that they'll have a higher probability of survival. There are many mechanisms that you can use to generate a particular correlation. Then the optimal correlation is going to have to be maximized over all of these state variables, and there's no reason why that surface ought to be regular in any sense, because you're talking about lots of different physiological features that will enable you to be a better forecaster. So in general, you can have a really complicated surface that looks like this. This is state variable 1, this is state variable 2, this is your correlation surface that you can generate from different kinds of state variables. The creatures that will grow the fastest, the behaviors that will be representative after many, many generations will be those that have maximum correlation. And given weird surfaces like this, you can have lots of different behaviors that generate the same growth rates. In other words, there are lots of different kinds of intelligence. There's lots of different ways to be able to generate these forecasts. And so that gives you a motivation for the fact that the bounds on rationality really can come about for lots of different reasons, for physiological reasons. Now, this is fairly theoretical, so I want to give you an example of a bound on rationality, your rationality. I'm going to do a little exercise and show you a video clip. Now, some of you may have already seen this, particularly if you've taken a psychology course. So by a show of hands, how many people have seen this video clip? If you've seen it, I'm not going to show it again. Okay, well, there are a few of you that haven't seen it. That's good. So let me tell you what I'm going to show you. It's a 30-second video clip of students passing basketballs back and forth to each other. And I'm going to charge you, those of you who haven't seen this, I'm going to charge you with the simple cognitive task of counting. Counting the number of times a basketball is passed from one student to another. However, to make it challenging, I'm going to ask that you count only those passes between students with white T-shirts. So for the purpose of this exercise, only passes between white T-shirted students will count. And the question is, how well can you do that task? Right? Now, you might think, well, gee, that's not very difficult. And in general, it's not. Except that while you're counting, I'm going to be counting out loud random numbers along with you. And you know how annoying that is when you're trying to concentrate? So I'm going to be actively trying to distract you. And the question is, how well can you keep your cognitive focus on the task at hand, okay? So let me start it up. Maximize this. Okay, everybody ready? Okay, here we go. So that's 1, 2, 3, 5, 7, 8, 7, 9, 10, 11, 13, or no, 12, maybe that was 11, 13, 12, 14, 13, 15, 14, 18. Okay. So for those of you who haven't seen this before, how many of you counted 13, 14, 15, 16, 17, 18, 19? Okay, there's some disagreement, which is a little disconcerting because we're all watching the same thing. Now, for those of you who haven't seen this before, did you see anything else that was a little weird?
Gorilla.
What?
It was a gorilla.
You saw a gorilla in the video clip.
Yeah.
You sure?
I'm not sure. I think I did.
So how many people saw a gorilla? How many people did not see a gorilla? We're watching the same clip, right? So you didn't see a gorilla. You're sure you didn't see a gorilla? Would you be willing to testify under oath that you did not see a gorilla? Yeah. Would you be willing to testify that you did see a gorilla?
Yeah, I'm almost sure. Yeah.
You're almost sure?
Money on the table, right?
Okay. So let me show you the same clip, and those of you who saw something weird, you can testify that this is the exact same video clip. There's no trick here. It's the same clip. This time, just watch, and I think you'll see something surprising. Without my counting and distracting you, and without your counting, you have a very different cognitive ability here. Not only was there a gorilla, it stood in the middle of the frame and beat its chest. And you didn't see it. You know, we talk about the black swan, but forget the black swan if you can't even see a black gorilla. Now, how could this have happened? How irrational, how stupid of you. But of course, it's not stupidity. It's the fact that there's a limit to your cognitive abilities. And I tasked you with counting the number of passes between white T-shirted students. And you did that generally pretty well. There were 17 passes, by the way. So you didn't do it perfectly, but you did it pretty well. But in order to do that, and in order to filter out the distractions that I was throwing upon you, your brain basically said, I'm going to focus on everything that's white and nothing else. By the way, this is one of the most important reasons why you should not be talking on a cell phone when you're driving. I mean, you could be thinking you're seeing the road, but if you're not focused on that little kid wearing that black raincoat in the dark of night, you will literally not see that boy when you run him over while you're talking on the phone. It's an impossibility to be able to see everything from a cognitive perspective when you are overloaded. If you're talking on the phone, the radio's going, the kids are screaming in the back seat, you are highly distracted. So the point is that we have amazing abilities as human beings, but those abilities are not infinite. We have finite constraints, and those constraints have an impact. So I want to take you on a brief detour of how the brain actually works so you can understand where some of these impacts and constraints come from. And to do that, here's a very brief lesson in neuroanatomy. This is a cross-section of your brain. It turns out that the brain is not nearly the homogeneous organ that we think of it as, but it contains lots of different components. So I'm going to tell you about 3 of them in particular. One of them is at the very base of the brain. It's called the brain stem, and it's probably the oldest part of the brain from an evolutionary perspective. It's the part that we have in common with both mammals and reptiles. All vertebrates have this brain stem. It's sometimes called the reptilian brain. This part of the brain is responsible for very basic bodily functions like temperature, breathing, heartbeat, all of the very, very basic aspects of being alive. On top of the brain stem sits the middle part of the brain, sometimes called the midbrain, sometimes the mammalian brain, because this part of the brain reptiles do not have. It's the part that is responsible for fear and greed, emotional reaction, sexual attraction, all of the things that we associate with warm-blooded creatures. You often heard the term warm and fuzzy, and in fact, we often feel much more kinship with mammals like dogs and cats rather than cold-blooded creatures like reptiles. And this is why. It's because the emotional center of the brain is based in that mammalian component. And one particular component is the amygdala. That's the part that's responsible for the fight and flight response, for fear and other emotional reactions. Finally, the third part of the brain that I want to tell you about is what we usually think of as the brain. It's that gray matter, the curly coils. It's actually not coils, but it's a tissue that's approximately 5 millimeters thick, the size of a dinner napkin, and scrunched up to fit in our brain casing, which is where all the wrinkles come from. That's known as the neocortex, and neuroscientists sometimes refer to it as the hominid brain because it's basically great apes and humans that share that part of the brain. And from the evolutionary perspective, it is the newest part of the brain, hence the term neocortex. This part of the brain is really responsible for what we think of as higher thought, things like logical deliberation, mathematical ability, language ability, all the things that are uniquely human reside in that neocortex. Now you might ask, how do people know this? How do neuroscientists figure this out? They figure it out using imaging techniques. All of you probably are familiar with magnetic resonance imaging. Some of you may have even had an MRI. That's where they put you on a table, slide you into a tube, and then they basically take pictures of you, not with X-rays, but with magnetic resonance imaging techniques. And what neuroscientists will do is take a subject, put him in the magnet, and take a series of pictures, in other words, make a movie of your brain while you're doing a certain task. And the reason that that's useful is because blood contains iron. Iron shows up on an MRI. So while you're engaged in a task, they can actually see where the flow of blood goes to your brain. So for example, if you're in the magnet and you're asked to read a passage from a computer screen that's projected into that tube so that you can see it, as you're reading, blood flows to the language area of the brain, which is the left brain. And so they say, the language area is associated with that. Now, why am I telling all this? It's because these three different components actually have different priority. Priority meaning they have different levels of importance to your bodily functions. For example, if you're in a car accident, God forbid, and you're bleeding and your body starts to go into shock and your brain shuts down, which of these three components do you think shuts down last? Which has the highest priority among these three components? Yeah, of course, the brainstem, because once that shuts down, that's pretty much game over. Your heart stops, your breathing stops. You can lose consciousness, which is part of the other components of the brain, particularly the neocortex. You can lose consciousness but still be alive thanks to this level of priority. So the brainstem has the highest priority. What about the remaining two? Between the amygdala and the neocortex, which do you think has higher priority? What would you guess? Amygdala. Why? You're right. That's right. That does have higher priority.
Help you get in there.
Well, that's right. The emotional centers are probably more important for survival than the neocortex. Also, from an evolutionary perspective, the amygdala is a lot older than the neocortex. Put another way, if you're being charged by a saber-toothed tiger, it's more important for you to be scared and run like hell than for you to be able to solve differential equations, even if you're from MIT. And so, in fact, it's true. The amygdala does have priority. And neuroscientists have actually figured this out in a very clever way. They take a subject, put them in a magnet, and they ask the subject to solve math problems, simple arithmetic, multiplication, division, while they're in the magnet. And as they're solving these problems in their head, they use their hands to control a cursor to be able to select the correct answer out of 5. As they're solving these math problems and using the neocortex, they'll take a pin and stick it in the subject's leg and induce some sharp pain. And the subject says, ow! And it takes the subject longer to solve these math problems. Now, you think you need a grant to figure that out? I mean, anybody could have told you that if somebody's trying to stab you, it's going to take you a little longer to concentrate on math problems. But here's the thing. What they found was that the extra time that it took them to solve the math problems, that phenomenon lasted for hours after the pinprick. Not just seconds or minutes, but hours later, it actually took these subjects longer to solve the math problems. And they can see that the flow of blood to the neocortex was constricted by this sharp stimulus to the amygdala. That's surprising. What that suggests is that emotional stimulus can physiologically limit your ability to use that neocortex. Another example that I suspect many of you have experienced, are currently experiencing, is when you're dating and you are trying to meet a very attractive person to ask him or her out on a date. So what do? You concoct a very, very clever way of meeting this person by accident. And then when you do, you're planning to ask them out on a date, in the most clever way to just impress upon them how wonderful you would be as a partner. So you do this. You somehow manufacture a chance meeting with this wonderfully attractive person, and you start talking, and the moment you open your mouth, gibberish comes out. You say exactly the wrong things, and it's a total embarrassment. Why is that? Have you ever wondered about that? It's because sexual attraction hits the mammalian brain, the midbrain. That's a very primitive response. And when that happens, it restricts the flow of blood to your neocortex where language ability resides. For all intents and purposes, love does make you stupid. And you see this. You've also heard the term, I was so angry I could hardly speak. I never understood that until I got so angry one day that I could barely speak. It's because anger stimulates the emotional centers of the brain, which reduces the flow of blood to your language centers. It does make it harder for you to speak. And this is directly related to Daniel Kahneman's notion of thinking fast and thinking slow. Fast thinking is thinking that's hardwired into our brain. And much of that hardwiring came early on in our evolutionary past, namely at that brainstem and midbrain components. The neocortex is relatively new. And in certain situations, these components fight with each other. Now, if you don't believe me, I'll give you another example that we can all do together about how these different components fight. This is a well-known psychological test known as the Stroop test. Some of you may have done it if you've done a psychological studies course. But let me show you what it is. I'm going to show you a bunch of words with different colors, right? Here they are. And what I'd like you to do is to identify the colors of the words from left to right as quickly as possible and say them out loud together with me, okay, when I tell you to. Don't read anything, just look at the colors and tell me what color you see as quickly as you can, okay? Everybody understand the task? All right, so here we go, let's go. We'll start with red, green, blue, orange, blue, brown, red, green, purple, pink, black, blue, yellow, green. Easy, right? Okay, same thing. Say the colors out loud with me as quickly as you can. All right, ready? Here we go. Blue, all right, black, all right. That's terrible. Way slower. Why? It's because in the first case, the color and the word agreed. Color recognition actually happens in the midbrain. Language ability resides in the neocortex. When there's agreement, you can do it pretty quickly. When there's disagreement, it takes your brain a split second to adjudicate that conflict. And you notice that in the delay. This kind of stuff happens all the time. And so the heuristics that we develop are essentially meant to balance all of the various different considerations within various changing and complex environments. So what I just described to you about getting dressed in the morning, the complex tasks that we face are much more challenging. And with these kinds of conflicts going on, you're going to see certain types of heuristics that are better than others, given a randomly chosen environment. Now, I want to go one step farther and talk about what economists think of in terms of decision making, which is planning, forward-looking behavior, and what ultimately I'm going to call narrative. It turns out that narrative is really the key to what we think of as rational expectations and intelligent decision-making. So to do that, I want to describe to you where the notion of narrative comes from, the idea of being able to figure out a sequence of events and be able to predict what's going to happen next. I'll show you a really interesting experiment that came out of some completely unexpected medical conditions known as split brain patients. So there are certain patients out there that suffer from epilepsy. Those of you, I'm sure, know, you've heard about it. Epilepsy is a certain neurological disorder that causes fits and seizures. The origin of epilepsy is essentially an electrical storm in the brain. Basically, electrical signals fire in an uncontrollable manner and spread around the entire brain, particularly the motor cortex, causing seizures and so on. And for certain patients that have what's called intractable epilepsy, there is no cure. There's no medical cure in terms of drugs that you can take. And so what they've developed is a rather medieval sounding therapy, which is they take the brain and they cut it in half. Now, it doesn't sound as bad as that, but it's pretty bad. As you know, the brain has two halves, the left and the right hemispheres, and they have different activities associated with them. The brain is connected, though, by what's called the corpus callosum, which is a very thick bundle of fibers, about 250 million fibers, nerve cells that connect the two. Epileptic patients that have intractable epilepsy, it turns out when you cut the corpus callosum and you disconnect the left and right hemispheres, that somehow reduces these electrical brainstorms and it eliminates their seizures completely. So after that, they can actually lead a pretty normal life. It's one of these things, I don't know how they figured it out the first time and who they got to actually experiment with, but whoever that person is should be sainted, because for all of the patients afterwards, it was an incredible godsend. Now, there's something interesting about these split brain patients, though. It turns out that they have certain deficiencies, and it took a while to figure out what those deficiencies were. And here's the deficiency. It turns out that the optic nerve is actually cross-circuited in the sense that what you see in the right visual field actually goes to the left brain, and what you see in the left visual field is actually projected to the right brain. Neuroscientists figure that out because they can actually see the wiring. They can trace the wiring and do experiments for that. Well, it turns out that for split brain patients, what they see in the left brain and the right brain are no longer integrated because the left and the right brain don't talk to each other anymore because they've been separated. And so they'll do experiments where they'll show a split brain patient an image that is split into the left field and the right field, and they'll show different images. And it turns out that the language center, because it's in the left brain, which is associated with the right visual field, when you show a split brain patient something in the right visual field, he or she can identify it and say, yes, that's a case. But if you show the split brain patient something in the left visual field, which goes to the right brain, where language ability does not reside typically, they won't be able to articulate what's in that visual field. However, when you tell them to take their left hand, which is their right hand, they can actually grasp something that is associated with that left visual field. I know it sounds confusing, so let me show you a very short video clip that actually highlights this. It's a fascinating set of experiments that has direct relevance for economists. So here's a video clip from YouTube. This is a split brain patient, and this research was done by Roger Sperry and Michael Gazzaniga. This is Michael Gazzaniga right here. This is a split brain patient. He was an intractable epileptic patient that had his corpus callosum severed. And now what they're going to show him is two things, one on the left and one on the right visual field, and you'll see what happens next. So clearly he sees the image, but he can't articulate that he sees the image, and yet when you ask him to draw with his left hand, he can actually draw the image, even though he's actually not left-handed, he's right-handed, but his left hand actually has the information. You can access it. But now something else is, that's even more relevant and surprising for economists. Let me show you one experiment that they did, but they didn't capture on video, but they wrote up in a paper. So here's an example of the kind of split field experiments they do. On the right, you have a chicken leg. On the left, you have a car buried in snow. So they'll show the split brain patient these images at the same time. And they'll ask the split brain patient, we're going to now show you 6 other images, and we want you to pick the 2, one by each hand, the 2 that are the most relevant for these images. Okay? So remember these 2 images now. And now here are the 6 images. Select the 2 that are the most relevant. Anybody want to take a crack at this tough experiment? The chicken and the shovel, that's right. Not surprisingly, the subject uses the left hand to pick the shovel and the right hand to pick the chicken, right? The chicken foot is on the right visual field. So the left brain sees the chicken foot, and the left brain controls language ability. So when you ask the split brain patient, why did you pick the chicken? The split brain patient says, because the chicken goes with the chicken foot. And he uses the right hand to select it. And now when you ask him, why did you pick the shovel with your left hand? You know what he says? The most amazing thing. He says, because the shovel is used to clean the chicken coop. That's what he says. He comes up with a reason for picking that shovel, because he can't, for the life of him, figure out why he would have done it. But his left brain constructs a hypothesis for why it happened. It constructs a narrative. And this has happened time and time again, where there's a clear reason why he picked the shovel with the left hand. But the fact is that he can't articulate that. And so this has led to the conjecture from Gazzaniga and Sperry that the left brain is really focused on constructing narrative, on hypothesis, on integrating all of these different observations, whereas the right brain is focused on sensory motor tasks. So the left brain is responsible for interpretation, for language ability, for executive function, for semantic interpretation, and it's the left brain that can actually be fooled into probability matching. It turns out that the right brain, when you focus on split brain patients and you give them probability matching tasks, the right brain visual field, the left visual field, actually does not generate probability matching behavior, except in one case. And that's when you use probability matching with faces as opposed to words. If you use faces, Brad Pitt versus George Clooney, it turns out that in those cases, probability matching occurs in the right brain as well. This tells us that what we economists think of as rational expectations is happening in a very specific part of the brain. It's the left brain. The left brain is coming up with hypotheses. And it will come up with whatever hypotheses it can, even if it has no bearing on reality, as we just saw. This was actually brought home to me in a very personal way when many years ago I had a research assistant bring me some empirical results. I asked him to run a few regressions and some analysis, and he gave me what I thought were some really counterintuitive results. So I stared at them for quite a while and ultimately came up with a magnificent explanation for what was going on. And it was a really shocking result that would have turned the entire profession on its head. That's how powerful it was. And then, yes, then the student said, oh, he actually had a coding error, and actually all the results were the other way. At which point I looked at the results, and I constructed a new hypothesis that was completely and utterly convincing for that. We do this naturally. We do this instinctively. It's part of what the brain does. It doesn't mean it's correct. It means that it's adaptive to our behavior. So the last thing I'm going to tell you about is now human evolution and what got us to this point. How did we develop this ability? And this is really critical for adaptive markets. Ian Tattersall, an anthropologist who was curator of the American Museum of Natural History, published a paper in 2008 on an evolutionary framework for thinking about the acquisition of symbolic cognition by Homo sapiens. It's a mouthful, but it actually was a very simple and earth-shattering idea. The idea is that there's a puzzle in the fossil record for humans. And the puzzle is this. 200,000 years ago, we evolved to the point where we were anatomically essentially identical to where we are today. But abstract thought, symbolic thought, did not appear until 80,000 years ago. If you look at the artifacts, you'll see, for example, certain kinds of tools, stone tools, that have these abstract patterns in them. This did not happen naturally. It didn't happen by accident. It's far too regular for this to occur. This was a fossil that was dated at 77,000 years ago. What happened? How did this strange gap in fossil history have an explanation? Tattersall had a conjecture that seems to be borne out by further evidence that has been developed since then, which is that somewhere between 80 and 60,000 years ago, humans developed the ability for abstract thought, that is, for conceiving of abstraction in our brains. And this idea of being able to engage in symbolic thought and symbolic computation changed everything. Because what it allowed us to do is to think about things before they happened and to make predictions about them and to be able to affect those predictions. In other words, forward-looking behavior and ultimately rational expectations. And of course, there was an explosion of cognition after that, including cave art, which is 30,000 years ago, and the pyramids, and writing, and of course, MIT. Wonderful, wonderful developments. Why is symbolic thought so powerful? Well, for the simple reason that it allows us to fine-tune our abilities via natural selection. Natural selection, not individual by individual, not species by species, but evolution at the very speed of thought. We can come up with 25 ideas and figure out that 24 of them are terrible, and one of them is worthy of a paper that we write and publish. That ability to be able to generate ideas and select among them has given us a tremendous advantage over other creatures on this planet. As far as we know, other creatures are not able to engage in evolution at the very speed of thought. And so the adaptive markets hypothesis is really applications of this framework to financial contexts. Behavior is produced by multiple neural components, and evolution shapes these components across time and circumstances. Evolution occurs at the speed of thought via narratives. We come up with lots of different what-if scenarios, and we pick the one that we think is best. We pick the one that we think is going to be the most important to us. And ultimately, rational behavior emerges from the proper balance of these components, but irrational behavior can emerge also when these components have improper balance. And what I mean by proper and improper is it's a function of the environment and the forces of selection on that environment. So I'm going to close with one example from finance, which is strategies that are uniquely proprietary and that ultimately become commoditized, alpha turning to beta. And the example I'm going to give is something that I think we all have heard about. John Paulson was one of the few hedge fund managers that bet against US residential real estate starting around 2004, 2005. And he bet against that not just a little bit, but in large size. And he actually ultimately made tens of billions of dollars for his investors and billions of dollars for himself in fees because of that bet. I would argue that in 2004, 2005, Paulson and Company, John Paulson's hedge fund, was unique alpha, unique investment expertise. He had a very specific view. He implemented that view. He bet in large size. He was correct. He made a lot of money. Well, at the beginning of 2009, Paulson's right-hand man, Paolo Pellegrini, who I don't know and have never met, he decided to leave Paulson and Company. I have no idea why, but I suspect that what must have happened is that instead of getting paid an obscene amount of money by Paulson, Pellegrini was only paid a ridiculous amount of money and decided that he was going to leave and go across the street and start up his own firm, which he did. He started Pellegrini and Associates, and he got investment capital. I think he raised $1 billion in a matter of a couple of weeks. Now, the investors that gave money to Pellegrini, it turns out that they actually didn't take money away from Paulson. They left money with Paulson, and they gave more money to Pellegrini. In other words, what started out as absolutely unique investment alpha ultimately became not so unique anymore, because now you have Paulson and Pellegrini and others. And The Greatest Trade Ever describes that dynamic. Greg Zuckerman's wonderful book that talks about the hedge fund industry and the mortgage crisis. There are lots of other examples of strategies that start out as unique and ultimately become commoditized. And this is the most technical slide I have today, which is that alpha that starts out as unique, when it's copied and duplicated, it becomes novel, but it's not unique. And after it becomes duplicated some more, it becomes popular and different colors. And finally, after it becomes totally commoditized, it actually becomes beta. I worked very hard on this to line this up, so I want you to appreciate that. Thank you. What starts out as alpha becomes beta, and ultimately, I think we have to think about exactly what the implications are for finance. Tomorrow, I'm going to talk about that specifically when we come to the hedge fund industry. Thank you.